Okay, this is supposed to be a straight wire, didn't come out all that straight. You got a bunch of little pluses here indicating charges. Okay, we'll just arbitrarily call it positive charge, could be negative. But it's a straight wire. Charge density is lambda. Lambda is charge per unit length. I'm going to impose this on the x-axis. The origin is center wire. So take an increment here. Delta x. And some point inside the end, which I'll call star or x asterisk. It's getting a little smudged there, but we understand we have the delta x interval with an x asterisk in the middle. I have a point here. If y equals a. So I want to figure out what the electric field is at this point due to the charge in delta x. What's the electric field at this point due to this charge? Okay, get a good response and say, well, you can't use Coulomb's law because it's not a point charge. Well, that's very good, but you can use Coulomb's law, treating this as a point charge, because, as I said, we're going to do calculus. We're going to be shrinking this interval down to point. So right now we can just treat this interval as a point. We're going to get an approximate result for the field due to this charge at this point. So we're going to treat it as a point charge. Okay. And I could say approximate point charge. Okay. And then you say, well, we need an R vector. It's an R vector that we kind of like to focus on. So we need a vector from here to there. Okay, well, what's that vector? Well, this vector is at coordinate x star here, and this is on the y-axis at point A. It should be pretty clear that the R vector is x star I plus a shift. So we got the R vector, got, well, what do we need next? Need I'm going to cut to the chase. We don't want to take too much time with this. Okay. Well, Coulomb's law is this, right? Okay. Electric field is a force over your test charge. I'm assuming big Q is a test charge out here, Q. So you can always invoke a test charge and then divide it out if you want to find the electric field. But you're going to get K times Q over R squared. And the R vector over R. Now, the book often writes this as an R hat, which is a unit vector, but I prefer just to write R over R, the R vector over its magnitude. But we understand this is a unit vector. Okay, so we got our R vector. K is the universal constant. What's the only thing we don't know? How long is this interval? Length is delta x, right?
Yeah.
What's the charge density mean? Charge per unit length. Charge is lambda delta x. And now, of course, we're talking about the field due to the charge in this increment, not the total field at this point. We're going to have to do an interval to get the total field. Okay, so there's your delta E. Now, of course, magnitude of R is xi star squared plus a squared. And I'm going to put these two r's together, make that an xi star squared plus a squared to the 3/2. Times r, which is then going to be k lambda delta x over xi star squared plus a squared to the 3/2 times xi star I plus aj. Okay, well, the rest is trivial. Total field at this point is the sum of all the field contributions of all the xi increments. Field at 0A is the sum of all the a lambda delta xi over a star plus xi star a squared plus xi star squared to the 3/2 times xi star I plus aj. This approaches the integral. Okay, well, I haven't put limits on this thing, but let's just say that over here is x equals negative L over 2. That's over here is x equals L over 2. this thing goes negative L over two to L over two. So we start by partitioning this interval from negative L over two to L over two into a bunch of small increments. Now, what we started with was we just started with one typical small increment. But it's understood that small increment is in a partition. It goes from one end of the wire to the other. Okay. That's why we start with a small interval. If we get the small interval, if we write out the expression for the small interval, then since we have specified that interval, we can write these xi stars here implicitly. We want to get that. Okay. I was using xi star just to mean x star. But without going into all the details, we have to go into to do this out of the calculus to find the effect of one small increment from the field at this point, and then we generalize that to any increment. So our x stars become x sub I stars. So we can say the sums from I equals 1 to n, where we have interval 1 here, interval n over there, and review your basic calculus if you don't understand that. And because I'm not going to have time to develop all that. I'm just going to use it. Okay, so we do this, and now our intervals become xi stars, and they run from negative L over 2 to L over 2, integrating k lambda x, k lambda dx over a squared plus x squared to the 3/2 times I plus aj. Now that's putting things in the same order I have them up here. But we usually want our dx out here at the end of our integral, our integrand, so that we know that we're integrating this x as well as this. Okay. And then we can simplify that just a little more. We can pull out the k lambda, see that we're just doing the integral of xi plus aj with respect to x. The integral of xi over a squared plus x squared to the 3/2 is a simple substitution. Just let u equal x squared, then du is 2x. In other words, just use your. Yep. I'll give you that one. Okay, we get k lambda times 0 from negative L over 2 to L over 2 of xi dx over a squared plus x squared to the 3/2 plus the integral from L over 2 to L over 2 negative L over 2 to L over 2 of a j over a squared plus x squared dx. And this is to the 3/2. I'll be able to read that 3/2, but you know that here. So you know what ought to be able, here. This integral just like u equal x squared, etc. And by symmetry, you get 0. Symmetry, because I've got this symmetric with respect to the y-axis, and the point y plus a is on the y-axis. Okay. Geometrically, you get vector components in the I direction pointing this direction from the left and pointing in this direction to the right. And for every increment over here, you've got an increment over here that gives you the equal and opposite x component. So your x components all add up to 0. Now you have to understand in terms of calculus where this adds up. It's going to be a u over a squared plus u squared to the 3/2. It's just going to be going to be an a squared plus u raised to the 3/2. And you do your trig substitutions and all that stuff, and everything works out. Over here, going to use a trig substitution. The a is just constant; it's going to come out. But you got this integral. These are pretty simple integrals. So that tells you what the field of a long straight wire is. Now your text does this too. But what I wanted to emphasize and illustrate is that you find a typical increment, figure out what the contribution to the field is, and you make that increment part of a partition, whatever to whatever, okay? And if it's a really long wire that you can treat as infinite, as long as A is a lot closer to the wire than it is to the ends, then you can do an integral from negative infinity to infinity. Okay. And also, that integral had better agree with what Gauss's law tells you, with the cylinder around the wire. That's pretty simple. Okay. Okay, well. It's an outline how I get the electric field of long straight wire. Read what the book said. Make sure you understand it, because then the problems are going to ask you to do things in other geometries. I want to talk about field lines just a little bit. Let's just say I have a positive charge here and a negative charge here. Then the electric field for the positive charge, well, it's radial, it goes out like this. And of course, it falls off. Okay. Then you have are not accurate field vectors. See where I'm going with this in a minute. But you get the idea. You got field vectors that fall off rapidly with distance. And the field vectors point toward the negative charge and away from the positive charge. Make sense? Because what's the electric field? Electric field is the force per unit charge on a test charge. If it's a positive test charge, it's going to be repelled from the positive and attracted to the negative. We generally assume a positive test charge. No real reason, usually, to think about a negative test charge. Okay. Now, when you get if these are equal and opposite charges, you see that up here at this point, or near this point. Matter of fact, I'll just kind of fudge a little bit. Say, okay, I've got a force here and a force here. Those two forces go together. Give me a force in this direction. Down here, again, in this direction. So all along this line, my force vectors are going to be perpendicular to the line. There's a symmetry that assures that that would be the case. So that now, these forces over here aren't much influenced by the forces of contraction to the negative charge. These forces of repulsion are much, much bigger than these forces of attraction would be all the way over here, because these points are so much closer to here than they are to here. What ends up happening? Well, okay, let's consider this force vector. Now, this force vector is going to be mitigated a little bit by the force toward the negative charge. The electric field of a positive charge isolated, no negative charge around, is going to have field lines that look like this. Okay, does that make sense? And the field lines are just lines in the direction of the electric field. In this case, this field line here, the field line would go like here. By the time you're out to this distance, you don't have a whole lot of force here. You've got a significant amount of force here. What happens is the field line starts out this way. It gets bent and then pulled into here. Does that make sense? Because of the influence of attraction from this field. It's a similar thing down. If I go up here, it takes a while before this thing is far enough away from this charge that the field you get, or the force you get from this charge, the attraction you get from this charge, has a big effect. So it's going to be a little more like this. And then you get something like this, something like this, something like this, something like this. Not very well drawn, it's a little too peaking right here and stuff. But you get the idea. You've seen pictures like this, haven't you? So you can see how to construct that picture because you have a straight line here. Okay, so these field lines give you the direction of the electric field at any point. Have you ever done this thing with magnetic clip with iron filings? You've seen how that kind of forms a picture of these field lines. This one is not a good line. The second derivative is too big. Okay. The field gets much weaker as you move away. and the field lines spread out. Density of the field lines gives you an indication of how strong the field is, the directions of the field line. Tell you the direction of the electric field. Okay. You can look at better pictures in your book and you can sketch better pictures. My pictures are usually better than that, but I'm trying to do it honestly. Okay. And you kept that thing straight a little too long. Okay, so anyhow, get the idea. That's what we mean by field lines, and they're important. For example, in Gauss's law, says that the total flux through a closed surface depends only is some multiple 4 pi k times the charge enclosed in the surface. Okay. Well, all the field lines that come from the charges in there exit the surfaces, don't they? Well, not all of them. You know, the field lines that exit the surface indicate the flux through the surface. We'll see pictures of that. Now, where I want to really go with this is the idea of a dipole. So here I have a positive charge and a negative charge. Acted, and there's some distance between them. What symbol do I want to use for the distance between them? That's a script L. Okay. So there's some distance between. I think maybe I'd want to use D, but I'm going to use the script L. Okay. Say this is your X direction. Then too many arrows in there. Then you've got an angle theta of this thing with the X direction. Okay, this thing's at some angle theta. Let's just say we have an electric field now. Call the vector field, call it E times the I vector. So it's in the direction of the x-axis. So what's going to happen to this dipole if it's not, it's just kind of a floating dipole. It's not necessarily fixed in any position. That dipole is free to rotate. What's it going to do? Okay. And what's its final state going to look like? Okay, well, I drew this a little bigger and I asked the question, okay, this thing's free to rotate, what's gonna happen to it? And everybody made suggestions and stuff. And if you're watching this video, think it through before you see what I have to say. But what's gonna happen, if you just break it down, is the negative is gonna be attracted toward this electric field, and the positive is gonna be repelled. So that this is gonna tend to rotate. Negative charge pulled to the left, positive pulled to the right. Okay, so net and ultimately, if it's free to rotate, it's going to rotate so that the negative will be in this direction, positive in that direction. It'll rotate till it's parallel to the electric field with the negative charge facing, well, with the positive charge. Uh, it'll align so that the direction from the negative to positive charge will match the direction of the field. The better ways to put that, but it's going to look like. Again, if there are no other forces acting. So that the torque is the magnitude of the torque. And while the forces are going to be equal and opposite, assuming these are equal and opposite charges. And uh, uh, and I probably ought to label these. I'm going to call this negative Q, all this and on. So this force is going to be negative QB. This force is going to be positive QB. And so now you have a torque about any point. Let's just consider this point. If this angle is theta, then in this case, torque would be QE sine theta times L over 2. And as I pictured it, that would be a positive torque, the counterclockwise torque. Okay. This would also be the counterclockwise torque. this. Now, what I really want to do is, I want to tell you that the vector torque equals what? What's our definition of torque? R cross F, right? Okay. So now if we have an R vector between these two, well, let's not use an R vector. Um, I'm just gonna write it down. Um, okay, I've just rewritten this again in an order. It's gonna make this a little more obvious. But it is mu cross E, where mu is called your dipole moment. The notation. Trying to keep the notation consistent with the text. So I'm just gonna call a vector from here to here, the L vector. So mu equals L Q. That's not the notation you got to see in your text. I should have paid a little closer to, attention to the standard notation. Okay. If I cross L with E, okay. The only thing I did wrong there, L has to go from negative to positive. Okay. So now when I cross L with E, I get a positive torque. Okay, now I'm actually going to cheat. Take a look at the standard notation so I can. Okay, now the standard notations, more or less standard. Instead of L, as I mentioned, I think kind of wanted to use D, so I'm going to use D here. Instead of U, we use P. Okay, so the same ideas, but the standard notation for the dipole moment is P is D times Q. Torque you get is just P cross E. And I think you saw that pretty easily. So if you want to replace all these L's with P's, can, but I'm not going to go through that. Every expression. The only difference between the notation, I guess I can, there's a L's that are following D's. Okay, now this applies no matter what the orientation of the dipole is, no matter what the orientation of the electric field is. Okay. Dipoles are a big deal. If we have a dipole, I'll draw along the x-axis, it's equally well drawn along the y-axis. On the left A be the distance between them. Question is, what's the field of this thing look like? What's the field of this thing at the point 0A? The R vector goes here toward here. Field contribution from the positive charge is going to be like so. And the field contribution to the negative charge is going to be like so. So the field is going to be like so. Understand what these vectors are. Get the field at 0A. I'm just going to write down the expressions. You're going to have AQ over square root of A squared plus B squared multiplied by it'd be A squared plus D over 2 squared. I'm not going to write this out just because of time, clumsiness, having to put in those fractions. You'll have questions concerning this. You understand, you get field here, you got D over 2 here, you got A here, so you know what the length of what this distance is, right? Square root of quantity D over 2 squared plus A squared. Actually, let me write it again. Yeah, I'm going to do it this way. This is okay. Put these a little further apart. Here's a point, let's call it 0y. Here is negative q, here's q. And this distance here is A. This distance here is A. So now if I want the R vector from here to here, it's going to be negative AI plus YJ. I want to do the R vector here, it's going to be AI plus YJ. Then based on these charges and these expressions, I'm going to have field out in this direction. I'm not trying to shortcut anything. E is going to be Q over squared plus Y squared to the 3 times I plus YJ. And in terms of what we wrote down previously, dealing with the line charge, it should be clear where all these things come from. It's going to be plus AQ over A squared plus Y squared to 3 times AI plus YJ. Meaning I could have factored out the KQ over A squared plus Y squared to 3 halves and just have this and this. And so a little space here, which will be Y squared to the 3 halves times two YJ. Again, it's just standard notation or something like this. You'll have problems like that. That'll be pretty straightforward. Okay. Um, what I'm getting here is a charge in the J direction. Carelessly, this should be negative AI minus YJ because the force is in this direction. Force this exerts is in this direction. So that's a correct expression. Thing that I want to point out is that this is not an inverse square force. A is constant. So let me write it over here a little bigger. Terms in the right order. Yet this expression, the terms in the numerator are just constant. Terms in the denominator are inverse cube and y. Because a squared plus y squared is raised to 3/2. And let's be clear about what I mean by this. If y gets big to the point where a isn't important, you have y squared cubed, y squared to 3/2, which is y cubed, right? If y is a whole lot bigger than a, e's pretty close to what you would get if you just ignored a, which is going to give you a y cubed in the denominator. In this direction, the dipole, the force, if the dipole's this big and it's over there, then we're going to be seeing an inverse cube force. We get close and it's still not an inverse square force, but the A becomes important and the Y becomes less important. And worry about that, but we're not going to analyze it now. Okay, well, that's one direction of a dipole. That's if you move perpendicular to the dipole along its axis. If you move along the x-axis, what's it going to be? Incidentally, the D for the dipole is 2A. I wanted to have A here and A here, so I didn't have to have denominators. I could have called this D over 2, called this D over 2. And you see I had a D over 2 here, I get a D squared over 4, be more confusing than X squared. That makes sense? So I wanted to change my notation around. Okay. Now, if I'm out here, F0, what's my electric field? Much simpler looking expression than this. Okay. Out y, x minus a, well, that's how far it is from a out to x, right? And from here to here is x, and I add a, and now I get the distance of this one. So that's all pretty simple. So this is kq times 1 over x minus a squared plus 1 over minus 1 over x plus a squared. That's k cubed times common denominator is going to be x minus a squared times x plus a squared. X minus a times x plus y is x squared minus a squared. So this is like x squared minus a squared squared. This is k cubed times what? Well, you square x plus a, you get x squared plus 2ax plus a squared. X minus a is going to have a minus 2ax. You're going to have an x squared for both of these terms and an a squared for both of these terms, but these both are going to be negative. You're going to have a 2xa here and a minus negative 2xa here, so you're going to get negative 4xa over x squared minus a squared squared. That's pretty simple, pretty straightforward algebra, but I've skipped some steps. So you might have to go back and listen to my words. Hey, just expand these things. And I think you get this. Do it yourself. Should just take you 2 minutes. Just write it out. Very straightforward. Instead of trying to look at this for 10 minutes and figure out what the heck I did, just write out what you get when you do this. You might not see as clearly where it goes, or at least where I think it goes. But you see that what you get down here, if you get far away where a is insignificant again, the denominator becomes like x to the fourth. Okay. Where x is much bigger than a. And the numerator is like a multiple of x. So it's going to be like an inverse cube again. Doesn't seem right. I'm probably thinking about a quadruple. But anyhow, do the algebra. The algebra is just, you know, it's a significant little bit of algebra, but it's just algebra too. This whole thing about dipole fields, you also have magnetic dipoles. So I thought we'd better talk about dipoles right now. This is a little more than what your textbook talks about with dipoles. They mostly talk about dipoles and torque. Okay. But later on, they develop it and do this thing. And I think in the problem sets, they ask these sorts of questions. And the questions that I've chosen to assign use the same type of analysis, which is why I went through this. Okay. So make sure you understand those steps. That's not how you turn off the recording. I'm not turning off. Okay. Very cool. I do. Here. Got an atom. Now, usually they have smiley faces, but you can't see the particles for the smiley face. So I'm not going to put a smiley face in. You got a nucleus here, an electron cloud around it. Okay. And it's nice and symmetric so that anything outside of this atom is not seeing an electric field. Make sense? All it's saying is a cloud of electrons, or just probability distribution for the position of electron, whatever you want to call it. The average distance from the electron, from the proton is in a hydrogen atom, dimension 0.529 angstroms, okay, in the ground state and all that stuff. Okay. Now what I'm going to do is I'm going to put a dot here for the nucleus. I'm going to make the nucleus a little bigger. So the nucleus is like the white. Should actually make it red. But the electron cloud, the center of mass of the electron cloud is at the same point as the nucleus, okay? Even though the electron is never at the same place. It's on this side, it's on this side, it's on this side, it's on this side. It's at this distance, it's at this distance. Okay. Now, if we put an electric field in this thing, okay, so we put an electric field. What does that do? Tends to pull nucleus this way, tends to pull the electron cloud this way. So nucleus gets offset from the electron cloud. Now we have a dipole. Called an induced dipole. Another example might be you've got a charged sphere. Or a metal sphere. You put an electric field in here. That electric field, it tends to pull more electrons this way. Okay. So it tends to pull your electrons this way, and it tends to give you a little more charge on this end. Now, I could shade it to do all kinds of things, but does that make sense? Okay, so I take something that's positively charged and move it close to these plates. Special positive charge, this side of this plate, leaving this side negatively charged, right? Okay, now what's that going to do? This. Well, that gets a little complicated. We're going to worry about everything now. Just the idea that when you have something with free electrons and impose an electric field, the electric field is going to pull those electrons toward it. Okay, that makes sense? That's an induced field. It's not like electromagnetic induction, which we talked about, but it's an induced field. It means if you have like two spheres and one of them's got charge on it, then the charge in this sphere is going to influence the charge distribution in this sphere. And the spheres will either end up repelling or attracting, and you can figure out which. Okay. We're not going to get into those details now because we're actually going to end on time.